Welcome everyone to this session about MicroTVM, an AI compiler for ARM microcontrollers. To quickly introduce myself, my name is Tom Gall. I'm the lead of the AI project within Linaro. And today we're going to talk about the TVM project as well as the MicroTVM project, which is a subset of the TVM project. So let's begin and introduce what is TVM. As I mentioned, it's an open source AI compiler. So by open source, what I'm referring to is the license that TVM is made available under. So all of the source code is available. You can build it for yourself. You can modify it. You can change it in any way you want. You can make those modifications available for others to go and take and use, or you can contribute it back into the TVM community. The TVM project is really a framework. So it's not just a single tool. It's a set of libraries. It is a set of capabilities that you get where it is able to import and digest a number of models from a variety of machine learning frameworks and do so in sort of an agnostic kind of way. And within this compilation stack that is TVM, then they have a variety of ways to target different CPUs and GPUs and offload engines that are available throughout the industry. TVM is a fairly new project. It's only been around for a couple of years, and it's just exiting what is called the incubation mode that it's been in as it's been getting started. So now it's sort of graduating into a more mature open source project within the Apache Foundation. As mentioned, it's under an Apache version 2 license. Within the slide there, it's on tvm.apache.org if you want to go and explore their web pages and their documentations and such. And as I mentioned, it does support a wide range of hardware from large to small. So let's dive a little bit more into the TVM architecture and why is it unique, and why would it be interesting to the ARM ecosystem? Well, first and foremost, as a set of tools and essentially a AI compiler architecture, it has the ability to digest models from a variety of AI frameworks. So this means, from the Onyx project, the Keras, MXNet, TensorFlow, TensorFlow Lite, it has the ability to ingest a model from any one of those projects. And that makes, TVM particularly quite useful for those wanting to do inference on ARM devices. Next, once you've ingested a model, what happens is that model gets changed into an independent representation, so an IR language, if you will. And then that IR language is able to be run through a variety of optimizers that then tune for what that model needs to accomplish in order to perform inference. And then the last mile is, of course, translation to your specific type of hardware. Now, historically, where TVM has been is on higher end pieces of hardware like ARM servers or Cortex-A devices. And so things on the lower end is actually something fairly new when it comes to TVM as a project. Now, lastly, I want to mention something fairly exciting and unique to TVM, which is on the right-hand side of this slide, and that is something called uTVM. It's an optimizer, and what it is able to do is it uses sort of feedback and goes through a set of successive iterations to optimize your code and end up with a faster performing, better performing model. And that makes TVM in many ways unique, where it's using artificial intelligence to end up with a better performing artificial intelligence model. We should think about the performance of TVM and compare itself to existing frameworks. So why would you turn to TVM as compared to just running something within TensorFlow or TensorFlow Lite? Well, as it turns out, when you use an AI compiler technology, you do accomplish better performance, and this is through that IR layer where a set of successive optimizations are made against a model, and it can make performance. I should say it can realize performance gains by making better choices for the optimized code that will be perhaps targeted at an offload engine, such as a GPU or a DSP or even a CPU. And so in this case here, what I've done is I've taken an ARM64 run that was done on a ThunderX machine, and I've just put in some comparative numbers. So we're using ImageNet, and this is a MobileNet version 1 all the way through MobileNet version 2, and then Inception version 3. And I'm just doing a comparison in the measurement of numbers where these are timed. So a lower number is better, whereas a higher number means that it took more time. You want inference to happen faster. And so, as we see here, that TVM is able to do quite well in its ability to optimize for ARM. And the great thing about it is this is TVM optimizing for AI inference. It's not TVM optimizing necessarily for an ARM processor. It's just being able to make good choices. Okay, so we've talked about TVM in general, but let's think about what this talk is all about, which is microcontrollers and devices in the small. So in this case here, I've got a discovery board. So this is the STM32F7 series, which has a Cortex M7 on it, and I happen to have one of the boards right here. And we're able to take a model, such as from TensorFlow, and using TVM, have the ability to run on this class of hardware. And we're able to do that through the MicroTVM project. So before we go in and explore what is the MicroTVM project, let's think about the problem space, especially associated with performing inference on Cortex-M devices. There are some special, unique cases that are different from doing inference on microcontrollers as opposed to doing something on a larger server. So firstly, as I mentioned with TVM in general, it has a advanced capability to digest models from a variety of different sources. And that in particular makes TVM quite unique. And when we're working with a microcontroller environment in particular, we have to be very cognizant of the models that we're importing in because of size restrictions. Oftentimes when you're looking at off-the-shelf models from some of the model zoos or some of the ones that you might create from the from like a TensorFlow project through a Jupyter notebook, those models are quite large. So, you need to go and oftentimes quantize your models. That means converting it from a floating point representation internally to something which is more based on integers to reduce the size of that model. And so this is something that, TVM, once you've done that quantization step outside, is able to blow in that quantized model and make use of it. Across the microcontroller landscape, there's a wide variety of ARM-based microcontrollers that are out there. There's of course, quite a number of AI frameworks that are out there, and there's a wide variety of ARM hardware that's out there. So, you take all of those things together, you end up with quite a Cartesian product of materials and different types of software that you may need to be targeting for. And that's pretty complicated to work with. And so a framework like TVM, which can output binaries, can help to make that easier. At least that's the vision going forward. Now, the other thing that you have in a microcontroller environment is we need to not just tune for time, but we also need to be thinking about the power that we're consuming. We need to be jamming ourselves into sometimes very aggressive working set size. We have to just, consume as small amount of RAM as possible. And we need to think about the offload that we may have available or may not even have available. Maybe we have to do the inference entirely on CPU, and we have to do that inference, at the same time that other things are going on within the microcontroller, such as working with sensors or what have you. So, these are things which are unique to the microcontroller environment. As I mentioned earlier, quantization is a particularly important thing that we need to do for running inference on microcontrollers. The size benefits that you can gain from slimming down from a 32-bit or even a 64-bit based model down to, something which is maybe fitting into an 8-bit byte or even maybe 4 bits, as long as you can, keep your accuracy up, that size that you gain is what is going to help allow your model to run on a Cortex-M device. As I mentioned, application logic is something that needs to sit side by side with where the inference is occurring. And since Cortex-M is often running maybe RTOS-less or even with an RTOS, we have to make that integration as easy as possible. So in supporting this this range of hardware and supporting optimizations which aren't just time-based but also power-based and such, there's a lot of unique issues that need to be delivered on when it comes to performing AI on a microcontroller. So let's now jump into MicroTVM as a project. And what does MicroTVM mean? What is it hoping to accomplish? Well, the very first thing that I want to make very, very abundantly clear is that MicroTVM is a work in progress. This is something that is gone from a proof of concept to now starting to be really alpha level code. It is not product ready. It is not something that you want to take and deploy in product. Not yet. Really, the vision of the project and the work ahead of us over the next few months is to graduate the code that's there, make it mature, and get it to a point where it is product ready. But I think it's important that as a project, this is something that is going to mature, it's going to be useful, and it's something that you're going to want to use in the future. And so I think that's makes it important to hear about today. So, thinking back to the prior slide and then thinking about doing inferencing on a microcontroller, what MicroTVM is really trying to accomplish as its main goals is we want to leverage the technology that's within the TVM framework. So this is the engineering that's been put into making a model run optimally and doing optimizations on that model and being able to use that on our microcontroller without having to engineer a whole new AI framework. Instead, we get to take advantage of the research and things that people have already invested and committed to the project. We need to have a minimal runtime. So we need to make sure that when we're doing inference using TVM that we're not incurring a large overhead in order to do so. We want to make that as skinny as possible. How do you talk to a dev board? Certainly when you think about technologies like JLink or ST-Link or what have you, there are ways that you can connect your dev board to a host machine and be able to do interactive development. Well, certainly MicroTVM needs to do the same thing. So we've approached this initially with OpenOCD and RPC to allow for interactive development. So that means you can be sitting here and working in Python to develop a model as well as an application and send that down to the device, test it, and get back results interactively. And that's a pretty important capability. Next is the RTOSs that are out there, such as Zephyr, Mbed OS, or FreeRTOS. FreeRTOS is another, just some examples. Or maybe you want to run RTOS-less completely. Well, if you're going to run RTOS-less, then MicroTVM needs to step up and provide at least the bare minimum that you would be able to run on a board in question. Then lastly, we think about things in terms of, well, what are the languages that an application developer are going to have to deal with? And so C++ and Python are really the two primary languages that MicroTVM deals with. And C is there as well, but really what you're going to end up doing is you're going to end up using C++ for the most part. So let's kind of look at the architecture and the development workflow of MicroTVM. So as mentioned, you have a model, you've trained this model, it's ready to go, and now what you do is you import that model, it gets transformed into Relay IR, and then the next step for MicroTVM is to transform the Relay IR into C++ code, combine that with the device support, any vendor support that you need, any environmental support that you need, compile that, and then ship that down onto the board. And then, of course, would go around in circles as you improve your code and hone in on your desired solution. So, this development workflow is one that is really optimized to be, as productive as possible. So let's talk about the binary that's going to actually find its way onto your end device. What does that look like? Well, there's really three components here, and they're separated by the three columns on the slides. So on the leftmost column, the low-level SOC control, this is your device startup. This is your peripheral support. This is the bits of code that go out and work with a sensor, do whatever that needs to be done as far as interacting with the board. And this isn't something that necessarily is going to be supplied by MicroTVM. This is going to come from your RTOS or your vendor, and it's really code that's engineered to do the right thing for the board that you're working with. The middle column is what empowers a couple of different things. So first of all, we have the runtime. So this is a MRSA-C runtime that just enables MicroTVM to be able to run on the board. Then there is the part that enables that interactive development workflow that I was talking about. So this isn't something that you would necessarily use in a production deployment scenario, but this is more when you're doing development. So you have an RPC server, and it's going and listening for you to push down new binaries. It's stopping as you need to, as it runs little snippets of code. And that RPC server takes care of all the framing and session information that would be associated with the work that you're doing. And then last, the third column is the compiled model that you have. And this is where you are your specific things that you're going to have that would be compiled for your board. And this might be CMSysNN as an example, and then it gets linked in and it's taking advantage of the RAM and the particular setup that you have. As far as maybe you have an offload technology that you can turn to, or maybe you're doing everything on DSP. Okay, so let's talk a little bit about where is the project today and how are we tracking things, and sort of what does the roadmap look like and kind of where are we going from here. So very quickly, the roadmap is available for public comment. It is posted publicly. It's been online now for several months. And so what you're seeing is the members of the project, we're all sort of jumping in and breaking off pieces to work on the various bits that need to be implemented. Internal to Linaro, and so Linaro is a company that's made up of member companies. What we've done is when we got involved with the MicroTVM project, we sort of stepped back and said, okay, well, what are all the attributes that we want to see within the MicroTVM project that would get this to be something that would be product level? So what we did is we developed a product level spec that talks about our own vision of where we want the project to go, such that it can be product ready and something that would be usable by Linaro members as well as the community and those people that would use MicroTVM in the future. And then what we do inside of Linaro, we have a weekly sync meeting that we conduct and just kind of keep in sync with each other, as well as coordinating our own activities. And then likewise, then there's certainly activity out in the community through the TVM forums where there's back and forth as far as what's going on. You have pull requests that go on, as well as comment on code as it's contributed. Okay, so next, what I'd like to do is go through an example of what does working with MicroTVM look like. And so this is the situation where, think of yourself as a developer. You're going to need to do inference on a dev board. The dev board that I've chosen here is the STM F7 discovery board. So again, that's this particular board that I have right here. It's a Cortex M7 based board. It is able to communicate via OpenOCD. So this is just done through a USB cable that connects to ST-Link on the board. And it makes for a really nice little board to do our work on. So in this case here, what I have is I'm going to work through a set of Python code that is going to load a model. Then what we're going to do is we're going to transform and compile that model. We'll send it down to the board. We'll then give that model a piece of data to use for inferencing, and then that model is going to turn around and it's going to give us a result or a prediction. And In the case of this Python code, there's a lot of the usual suspects here that if you've been doing inference or working in AI circles for a while, you'll probably immediately recognize things like NumPy and so on and so forth. So in the case of TVM and the TVM libraries, we have something called TVM Micro. So we go ahead and import that in. The TVM contribute libraries, they have the ability to pull in test data for us, as well as pull in our model and do the load from TensorFlow. So in this case here, I have a TensorFlow Lite model that I have already gone and tuned and created. It's a very, very simplistic model. It is something where we give TVM the TensorFlow Lite binary from the model, and we just go ahead and load that into memory into a flat buffer. And once we've done that, then what we're going to do is we're going to transform that model into IR. And so in this case here, we've loaded it into memory, and then with the tflite.model.getRoot model, then what we're doing is now we're going to set things up such that we can parse the model. So the very first thing that we're doing, just as a kind of a bit of debug, is that turn around and ask the library to make sure that what we've loaded, does it recognize it? What version of the model is it? In this case, this comes back and tells us that it's a version 3 TensorFlow Lite model. Okay, so now what we're going to do is we're going to transform the model from a TensorFlow Lite object into a Relay IR model. And so in this case here, what we have to do is we have to tell the system a little bit about the model. So in this case, what are the inputs? So in this case, the input is a 32-bit floating point value. It's just 1. And the name of that input tensor is called dense_4_input. And then we go ahead and pass this information in with the shape dictionary and the type dictionary, and then we receive back what we need in the form of the model and the params. So next, what we're going to do is we're going to set up the actual target device. And so in this case here, we're saying that our target is going to be C code, and that the device is going to be a TVM micro device. And then next, we specifically will set up a type, a hardware piece of hardware that we're going to talk to. And so in this case, it is a STM32 board, where we're creating a device configuration. And with that device configuration, then we're going to set up a MicroTVM session. So this is setting up our interactive session, which allows us to send binaries down to the board, as well as data, and being able to run the model. Then lastly, on this slide, what we're going to do is we're going to transform that model. We're going to turn it into basically a binary, something that we can ship down into the device. And so in this case here, before we start and do that, what we're doing is we're going to create a transform object, and we're going to set the optimization level, but then we're also going to turn off 2 things. So as it would be working with the model to optimize it, we're going to specifically disable fusing operators, and we're going to disable vectorization. This is a specific choice that we're doing because in the current state of MicroTVM, if we turn these things on, things will crash. So there's some issues that we need to work out with that before we enable those particular abilities. Next, we're going to do is we're going to build our Relay IR. So this is using the model and the params that we got earlier. So using those passing in those 2 objects, then we're going to do is we're going to get a graph back, and we're going to get the C module that is nearly ready to send to our target device. And so now with the create micro mod, so now we're creating the module. So this is now, we're going from C code to binary. And this is then going to be specific for our board and ready to send down to the device. So this creates the first step, the create micro, is what's creating the binary. And then the next step is creating the runtime. So now we're getting ready to run our binary. We're connecting with the context of running that binary. Now we're ready to run. And so after this create step has been done, what we can do is we can set the input value to our model. So this is going to be a value that goes into the input tensor, and what we need to do is now do that in the form that the input tensor needs. So this is the kind of the next two statements in the middle of the slide, which is set the params. So we're just kind of basically kind of connecting two dots here, and then we're going to create an ND array, which is made from an NP array, and it's that single value. It's just a 0.5 with a floating point value of 32. And once that is set, the value is put into the input tensor. It is then sent up to the board, and so mod.run, now we perform inference. So what we're doing is we're asking, run the model, give us a prediction, at least as far as, you know, what it should be predicted. And then once we return from run, then what we're doing is we're going back out to the device, and we're going to get that result back and then print it out to the screen. So in this case here, it's a very boring value of 0.5. So in this case here, the model, really what this is doing is it's modeling a sine wave. So when you put in a value, it will try to predict what should be the next value in the sine wave. And so we just get it from the output tensor and write it out on the screen. It's, in the grand scheme of things, a kind of a very contrived example, but it does show how you can consume a TensorFlow light model and get it into MicroTVM and be able to run it on a board in just a few lines of Python code. Okay, so in summary, what I want to do is leave you with a few things about how to get involved with the project. So, you know, maybe you're somebody who's a bit more advanced in your interest in AI, and you'd like to get involved with the AI project, or with the TVM project, and make some contributions. So the source code is available on GitHub. It's very easy to go out and get that. We have a contributor's guide as part of TVM. So this tells you how to format your patches, how to go through the process of contributing them and making them available for GitHub. You know, basically what we do is we use pull requests. As far as an interactive ability to have conversations and propose ideas or talk about problems that you run into, that's what the discuss forums are for. There is also a Slack channel that is available. It is not as active as the discuss forum, so I would actually ask that you probably go to the forums as a default communication path. However, there are a few of us that do hang out on Slack who work on MicroTVM or just are within the ARM ecosystem, and certainly, you know, the more the merrier. We welcome you to come and join us. If you have bugs and issues that you discover with TVM, again, the GitHub system is what we use to track those. So that's my presentation. I hope you can find some interest in MicroTVM as a project. I really encourage you to kind of keep an eye on it. I look forward to hopefully coming back at a future date, and, you know, either through ARM DevSummit or other avenues that we'll be able to sing some praises of what's been going on with MicroTVM and the next involvement as this project evolves and becomes something that is useful to you and your products as you do inference on microcontrollers. So thank you very much.